All right, what's up, guys? Thanks for coming around. This is going to be the Bio-Chem discussion club. Now, there's a little bit of a thing with the physics discussion club wrapping up and all that. So we'll take 1 or 2 minutes to see if anyone else is coming in. But in the meantime, what I want to do is screen share this question for you guys just to consider for the next minute or so. This is a question from the 2021 AP exam. So quite recent, and it's going to kind of segue into our discussion for today about stoichiometry and also perhaps an intro to biomolecules. We'll see what we'll be able to discuss in this time. But anyway, check that out. And what I'm also going to do is in the chat, I'm going to put a link to a Google form. If you guys could also fill that out, that'd be good because it's just for me to get some information about where everyone's at with in terms of chemistry knowledge and in terms of bio knowledge. Actually, before you guys fill that out, give me one sec. Gonna check something on the phone. All right. Okay, I'm gonna screen share that question real quick again. Yeah, just check that out. All right. Anyway, let's get started. So, for those of you who have filled out the form, from what I can tell, this is a fairly new group to chemistry and or perhaps to biology as well. So I think we'll take it a little bit slower. And if we're able to solve this question by the end, I do think we will be able to solve this question by the end of today, depending on what we're able to discuss. But anyway, you guys might notice that Ethan is currently in the room. Ethan's my brother because I am borrowing his iPad. And that's so that I can screen share from here and it just makes writing a lot easier. So that's who that is. But anyway, I'm gonna share from his screen and let's get right into it. So this right here is basically just taking the problem that we had before about um, about the certain kind of precipitate reaction, and the question was asking a lot about what the equation is and how the precipitate balances out, and ultimately it's looking for the molarity of the solution. So some things I've written out here is basically to represent this chemical equation, and um, this right here, hold up. These right here are the chemicals we're talking about. So when we write something like CuSO4, that's basically shorthand for a certain kind of chemical. Each of these symbols would, of course, be representing something. Cu, perhaps some of you guys might know that as copper. Yeah, indeed, copper. Anyone know what S is?
Sulfur, I think.
Sulfur, yeah. And what about that O?
Oxygen.
Oxygen, yeah. So what we have right here is copper, is a compound with copper, sulfur, and oxygen. And this particular compound is going to be called copper 2 sulfate, just a name. And we can see the word copper here, sulfur. The H is actually including the oxygen, but that's a story for another time. But what we see here is a representation of a chemical compound. BaNO3, barium nitrate, is very similar, just compounds. And I'm wondering, what is our familiarity with the periodic table? Do you guys know how to use a periodic table and read it, or is it something?
Yes, I think.
Yeah. All right. Amos.
I would say I'm fairly familiar with it.
All right, that's good. So then, if I were to share this screen right here, this is just your responses. But over here, this periodic table, P-table, is an online periodic table that provides a heck ton of information, as you guys can see. And right here, we see a representation of all the elements. And of course, this is a very purposeful kind of arrangement. We see that the mass of the elements, which is down here, like the 1.008 or the 22.99, all those are masses for each of these elements. They all have their own meanings. Masses go down somewhat like this, and they are, of course, ordered in certain groups. These are all purposeful things. Probably something we'll examine either next time or the time after. We'll have to see. But what we can see here is we'll be able to find the specific elements that we were talking about in that other question. Copper right here. Oxygen is over here in the green. Sulfur around here as well. Barium's over here. So these are all elements that we're familiar with. These are all specific kinds of compounds, or well, they come together to make compounds where we can predict their behavior because we understand these elements. And this periodic table will, of course, show some of the information that we understand about these elements. The mass, perhaps the state of matter at room temperature, different things like that. But anyway, let's go back to that equation that we had and see what we understand about it. So sharing this. All right. So let's take a look at this equation right here. Here we have CuSO4 AQ plus BaNO3 AQ goes to, or the arrow pointing as a reaction occurs, BaSO4S, and then CuNO3 AQ. So here we see those compounds that we looked at briefly before, CuSO4, BaNO3. On the other side of the arrow, we see a rearrangement of these, because a lot of chemical reactions are just that. They're just rearrangements of the different atoms we see. Now, what else do we notice about this? Well, what I see is this AQ. I wonder, do any of you
It's
guys
an aqueous solution, I think.
Yeah, aqueous. So aqueous meaning water, so in water or dissolved in water in this case. So right here, very simple representation of CuSO4. In reality, this is going to be a 3D lattice structure of atoms, an organized three-dimensional structure, molecularly, of course, on the microscopic scale. And what happens when we dissolve it in water is that these different atoms are going to separate in water. So if I take this right here, move it over into this imaginary beaker I have over here, they're going to separate. So let's see if I can do this properly. And the reasoning behind this is a lot to do with energistic kind of significance. So the bonding between these atoms with water and other kinds of molecules, that's going to be what ultimately results in this this separation of atoms. So this is all going to be within our solution discussion a little bit further on. But basically, what we need to know here is when we see AQ in a chemical reaction in a chemical equation, that's going to mean aqueous, and that means within water. So these molecules are now within water. BaNO32, similarly, they're going to be within water. And since BaNO32 is a very similar kind of compound to CuSO4, it's going to behave very similarly in water. And you might ask, how do we know it's very similar to CuSO4? Well, I see a metal and I see a non-metal, and they're balanced in charge. Now, all this might be kind of babble to you guys right now, but that this is today really what I hope to do is kind of show you the wide spectrum of different things that we have to cover, while also covering some fundamentals. So stoichiometry is going to be a word that's not only big but also meaningful to you guys by the end of today. Anyway, back to this scenario, we have AQ for both CuSO4 and BaNO32. Right here we have an S, so I wonder, does anyone know what the S stands for?
Solid.
Solid. Yeah, so a solid is what comes out of this reaction. So we have aqueous, 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 and this solid. So BaSO4 is what ultimately forms the solid, and BaSO4 would be, based on these arbitrary colors I picked, it'd be black and red. So while I'm doing this tedious dot moving process, we'll talk about what's going on here. So does anyone, perhaps someone might know what kind of reaction this might be called? There's a very specific kind of classification. No, okay, so this is what's called precipitation reaction. Now, in a usual precipitation reaction, you wouldn't have 8 dots or 8 atoms to work with. In reality, you're going to have trillions of atoms, probably more than trillions of atoms, all combined in these larger structures. And a precipitation reaction is where you have many things that are dissolved in water, but some of it comes out of the solution, comes out of the water solution, and forms solid. So in this case, we see BaSO4 forming a solid. The rest of the stuff there, so the copper and the nitrate, that's going to remain in the solution, just kind of floating around, minding its own business. And then this might make the other question, why does BaSO4 specifically come out of the solution as a solid? And why does the other stuff stay in the water? Once again, it's going to derive into energy bonding principles. And what you guys are going to find out soon is that learning chemistry means that when you learn it in the beginning, you're going to be taking a lot of stuff for granted. That was one of the things that annoyed me very much when I was first learning the basics of chemistry. But I promise you guys that sticking with it, sticking with our discussions and learning further by yourself over the next few classes, I think, the next few meetings, I think that would be a lot of this stuff will start to make sense, and there'll start to be the reasoning of why does this happen. You guys will be able to answer that. But right now, what we know is that these atoms and compounds and ions and all different kinds of things in the water. Right now, we have 4 of them: copper, sulfate, barium, and nitrate. And the barium and the sulfate are going to come out of solution as a solid. We see this representation right here, a little bit different, shorter primarily. But what do you guys see about this one? What's different between the second equation we have and the first?
Negative and positive charges.
Negative and positive. That's good thing to point out. Anything else?
By first equation, you mean the big one on top, right?
Yeah, this one right here.
There's the extra copper CuNO3.
Yeah, right up here, this first equation we see the CuNO3. So these are actually two different representations of the same kind of reaction. We see that in both reactions, we are eventually producing the BaSO4 that's solid. So both of these are what are going to be considered precipitation reactions, stuff coming out of water. The same reaction, except that with the second reaction, essentially what's going on is you cut off a bunch of the irrelevant things. Irrelevant being a term that I think isn't a great descriptor, but basically a Cu and NO3, they're not doing much in solution, right? They're not really participating in any significant kind of transformation. That's what the Ba and the SO4 are doing. So they're actually what are called spectator ions. If I can change off the highlight, spectator ions. Just a name to say for those things that stay in solution, mind their own business. So that's why in the second representation, it's a bunch more condensed, where you're focusing on the things that actually change during this reaction. Angelina pointed out the charge, so the 2 plus and the 2 minus. That's pretty significant as well. So in reality, these ions, all four of these ions, they have their own charge. Cu is 2 plus, SO4 is 2 minus, Ba is 2 plus, and NO3 2 is 2 minus. Notice that in each compound, they're balancing. So the 2 plus and 2 minus for both of these compounds, they balance out. Same thing goes on for the BaSO4. And then that might also beg the question, what are these 2 plus 2 minus things? What do they mean?
Electronegativity.
Electronegativity. That is one way to put it. Oxygen does participate in various reactions involving the consideration of electronegativity. But the one I want to point out for today is if we look at Ba, second row, second column, I should say, second column over here, that's going to be indicative of 2 plus charge. Sulfur over here, sulfur would be 2 minus charge. In this case, we're actually dealing with an ion, SO4 2 minus. So this one's actually going to be a very specific kind of compound that is 2 minus overall. But anyway, for majority of atoms, though, if they're by themselves, say like potassium in a certain kind of compound, you can kind of predict what its charge is going to be in that compound, depending on its position. So K is going to be 1 plus, Ca is going to be 2 plus. Over here, we're going to see that there's going to be some minus. So Br would be minus, bromine 1 minus, selenium 2 minus. In the center, it gets a little weirder. For example, vanadium, it could be 2 plus, 3 plus, 4 plus, or 5 plus. It's got all those options to itself. Iron could be 2 plus or 3 plus. And copper is 2 plus, can also be 1 plus. So I do want to point out that pattern where looking at the column placement can help you determine charge, but it's not the ultimate determinant. There's a lot of other things going on. This column right here, helium, neon, argon, things like that, those are going to be what are called noble gases. And that just simply means that they usually don't take on a charge. Now, many chemical reactions are going to involve charged ions interacting with each other or the transfer of charge. So in this case, we see charged ions interacting with another, with the barium and the sulfate, and them doing weird things in water. What happens with these compounds, because they don't usually carry charge, is that they usually don't participate in reactions, at least not too often anyway. So I'm going to stop that and get back over to the iPad. All right. And that's the basis for that charge. But anyway, transitioning over to this, which I just basically rewrote that upper equation, but now we can look at it in more detail. So let me pose a question to you guys. Let's say I have 1 mole of barium, 1 mole just being a unit of measurement. So alternatively, I could probably say, for the same kind of aim, I'll say let's say we have one atom of barium and one atom of sulfate. Well, that wouldn't be an atom, that'd actually be an ion. But let's just say we have one of each, is what I'm trying to say. How much of this compound will we be able to produce? How much of this specific kind of formula?
1.
1. I'm going to take off the atom and ion stuff because for our intents and purposes, that part doesn't really matter. We have one of each, and they put together to make one. That just kind of makes sense. It's like putting together Legos, or you have one pencil, second pencil, put it together. You got two. That's the basic idea, and it does work out because there's this idea called conservation of mass that I'm sure all of you guys know intuitively. The conservation of mass just meaning if I take any kind of physical object, break it apart, the mass is going to all be there. Now, maybe you broke into many pieces. All the mass will be then distributed over all of those pieces. Mass doesn't disappear or appear out of nowhere, right? Now, of course, when we get into more wonky things, so if we get into, say, radiation or quantum mechanics, then this idea of conservation of mass goes out the window. But for ordinary kinds of chemical reactions, more everyday objects, everyday life, and other like ordinary chemical reactions, we're going to see that conservation of mass is very important. And that's what we see right here. This reaction holds so that if you have one barium at the beginning, you end up with one barium at the end. One Ba means one Ba on the other side. Same thing with the SO4. Now let's say I have two Ba atoms, and I still only have one SO4. Now, how much of this compound will I be able to produce?
1.
1. Yeah, exactly. Because just because I have two Bas doesn't mean that I'll suddenly get more SO4. So, of course, I'll have a Ba left over, but conservation mass still holding true. Now, if I were to change this to 2, then we'll see the outcome is a little different. If we go to 2 right here, we'll have 2. And this is, of course, assuming that the reaction happens completely. Now, let's say I have, I don't know, let's say I have 6 times 10 to the 24th molecules. This is not a random number. I'll go into it a little bit. 7 times 20 to the 24th molecules. How many BaSO4 units will I be able to produce?
6 times 10 to the 24.
6 times 10 to the 24th. The exact same principle still holds true. You're taking the lower number, and that's kind of the limit for how much you can reduce because conservation of mass. SO4 2 minus not going to suddenly change into Ba2 plus. So, of course, we'll have another 10 to the 24th SO4 2 minus left over. This is assuming a complete reaction. That's assuming that if you have a certain amount of Ba, certain amount of SO4, and you put them together, all of it forms this new compound. And that's not always true because there's something called an equilibrium where while these two compounds are forming together to make this one larger compound, there's actually a reaction going the exact opposite way, where some of the BaSO4 is breaking apart into Ba2 plus and SO4 2 minus. The fact of the matter is that depending on how much you have of this, and that, the direction of which reaction is more powerful to dominate the other, that changes depending on how much you have. So let's say I have like a ton of BaSO4 and very little SO4 2 minus and very little Ba2 plus. Then a lot of it's going to probably break apart, decompose into its component to parts. So alternatively, it could go the other way. So that's what equilibrium is about, and also indicates that never will you actually have all of it go to one direction. Of course, for our purposes right now, we're going to assume complete reaction. We're going to assume 100% yield. 100% yield just meaning you get all of the product you're looking for. All right, now if I go down to this equation right here, of course, this is that bigger equation we saw earlier right up above over here. Same thing right there. I think we've looked at this equation quite a bit, but let's take those principles we had before, apply it to this scenario right here. Now let's say I have one BaNO32 and one CuSO4. How much BaSO4 am I going to get in this particular reaction?
1.
1. Exact same thing still happens. We only have one Ba and one SO4. You only can make one BaSO4. We're also going to see we're only going to have one CuNO32. All right, I think we're pretty good with this. So now let's put together something a little bit more interesting. Let's do that. And no. There. So now we have this equation right here. CH4, we haven't seen that before. CH4.
Methane? Is that methane, I think?
What's up? What's nothing?
Is it methane?
Methane.
CH4?
Oh, I thought you said nothing. Yes, CH4 is methane. So we have this compound called methane. It's a gas, greenhouse gas. You guys might have seen it on the news. Methane is really bad for the environment, all that. But methane, and we have O2, oxygen, forming CO2, which probably some of you guys recognize. That's carbon dioxide. And then we also have H2O. That's pretty familiar, water. So this reaction going on right there. And I put a 2 in front of the O2 and the H2O because let's say I take those away. Then what we see is that conservation of mass doesn't hold up. Now, can anyone tell me why? What's going on right here? Why would this equation not be valid in a sense?
You need to balance it.
Yeah. So if we look over here, we have two O's, right? O2, that's going to be two oxygen atoms. And here we have O2, so that's another two oxygen atoms. But here we have a third oxygen atom. Conservation of mass tells us that's a no-go. So in order to balance it, I can put these two tubes in front. When the reaction gets more complicated, the balancing becomes a more complicated process. This one is a little bit straightforward. You can kind of see what works and what doesn't. For example, you can see that over here, there's no H's. So therefore, all these H's would then contribute to these H's. I think it can balance and so on and so forth. Quite doable. For more complicated reactions, it'll be a little more difficult, but we'll get into that in a little bit. But with this one, if I were to have one of these, three of these, what would be my products? How much of these products would I have?
One
what?
I mean, you wouldn't be able to make it, right? Well, there would be one of CO2, and then there wouldn't be, no, there would be one of H2O2 or 2H2O, right?
Two H2Os, yeah. So what we see here is that we have one of those three of these. We need at least two of these to combine with this one of these, and then we're out of CH4. So this would be the limit. The CH4 would be the limit. Now, this is what's going to be called the limiting reagent. I'm just putting that name to that concept we've been working with. The one that is the upper bound on how much product you can produce, that's going to be the limiting reagent. In this case, that's CH4. These 1 and 2 will then be able to produce one of each of these units. So we'll produce one CO2 and one of this. So we'll actually produce two H2O at the end of it. So that's where that 2 comes in. All right. Just to get rid of this stuff. And what I think we'll do is we'll turn to that question we saw at the beginning of today's. Now, Suyan, I'm not exactly sure what the accents are on your name, so I don't even want to try. But if you're there, what we like to do here is participating is a big part of our discussion club. So the question that I showed at the beginning of class, I know you probably might not have seen it, but I'm going to share it again right now. So feel free to take a look, read through it, and see how much you understand, and then we're going to talk about it together and work through part of this question.
Okay.
All right, so one thing I mentioned at the beginning of today is that this reaction that I was working with as an example, the CuSO4 and BaNO3 and all that, those I took from this example so that we could connect it right back to here. So what I'm going to do is I'm just going to write that equation out again. So CuSO4 plus, and this time I'm just going to leave off the states of matter. So the little parentheses with the AQ and the S and all that, I'm just going to leave that off. Usually you want to write it as many as like whenever you're writing a reaction, you want to write it typically. Sometimes you're unsure of what the state of matter is. So in that case, you might not. It's really a situational kind of thing. But anyway, let me finish writing this. All right, so that's our equation that we're dealing with right there. So hopefully you guys had a chance to read through this. What's going on here is a student having this lab demonstration, a very common kind of AP problem where they try to contextualize what's going on. They want to put their question in context. So right here we have this reaction that the student's doing. Determine the molar concentration of a CuSO4 solution. Okay, and then we have this precipitation experiment where they're adding BaNO3 to this CuSO4, and of course a reaction occurs, and we have a white precipitate. Now that white precipitate is going to be our BaSO4, it's going to be our solid. The student filters the precipitate and dries it overnight, and there's this data. Then you might ask, what's the drying about? That's because this solution or these compounds were in water. So what sometimes happens is that when you take it out of solution, even if you take a whole solid out of solution, it's probably going to still be wet. So you don't want that water, that extra water in your compound to factor in to the mass that you're measuring, because it's not the actual solid, it's water that happens to be inside the solid. So that's where the drying comes in. It's just part of the lab procedure. Anyway, we're given this data, and we're asked to write a balanced net ionic equation for the precipitation reaction. Now, I haven't told you guys what what balanced net ionic equation means, but we've talked about all the stuff, all the principles for this. So I wonder, does anyone want to have a go at either writing the equation or explaining what balanced net ionic might mean? Either of those would be good.
I think I forgot I did this a while ago, but I think that the net ionic equation is where you find the precipitate and cancel out all the spectator ions and stuff.
Yeah, exactly. I like how you mentioned the precipitate, spectator ions. Those are all good stuff. Spectator ions in this case are put all the way down here. That's going to go away, and they're going to go away from these sides of the equation too. Now, of course, we're going to add the charge, and we're left with our balanced net ionic equation. The balanced part just means that you want to have coefficients on both sides so that everything cancels out. So if we take our methane example, the Ch4 plus O2 goes to CO2 plus H2O. This would be unbalanced, and we'd balance it like so. So that's just what balancing means. Right. And also, by the way, that methane reaction, that's what's called a combustion reaction. Basically, you can imagine it like you have methane in a tank or something. It's a gas, so you hold it in some kind of metal tank, and you light that methane on fire. That's basically what the reaction is about, right? You might notice it requires oxygen. That means you're burning something. Usually when oxygen is consumed on one side, on the left side of the equation, that means you're going to probably be burning something, most likely. And then we also see that carbon dioxide and water are produced. That's a sign of a combustion reaction. So yes, when you're going camping at night or something and you light a fire, the fire is producing water, but it's producing water vapor, most likely, because it first comes out as liquid water, perhaps, but then all those water atoms are, all those water molecules, molecules are energized, so then they are evaporated. Anyway, a little tidbit. But here we have our balanced net ionic equation. Basically, we just take off the spectator ions, as Suyang said, and what we're left with is the ions that are actually participating in the reaction. As such. All right, calculate the number of moles of precipitate formed. All right, now we're starting to get into some nitty gritty, but does anyone have any ideas before I get into this question? Any ideas? And I think it should be nice and clear that we're going to be using this data for this second part. How can we do this?
I think this has something to do with like molar mass.
Mm-hmm. Molar mass.
Yeah, so to find the number of moles of precipitate, you have the balanced net ionic equation. I have I guess, unique way of doing it. I don't know if it's like traditional, but basically what I do is we have to find the number of the moles of the precipitate, and in this case, I think the precipitate is like like barium sulfate, right?
Barium sulfate, yeah.
Right. So then I just need to find the molar mass of barium sulfate, and then divided by the amount of barium sulfate produced, like to get moles, and then can like balance it out on the other side as well. I think something like that. I have to write it down though.
Yeah, well, that's a pretty perfect set of steps that you described to us there. A lot of big words there, though, that I haven't exactly covered yet. So, but we're gonna walk through it, just as you said. So, first step that Yang pointed out to us is we have barium sulfate, and what we can do is take its mass. Oh wow! Hold up. Let's make that thing. Mass of barium sulfate divided by its molar mass. Molar mass, in a nutshell, what that just means is, if I'm going to share the periodic table real quick. We have the masses of each of these individual atoms. They're what are called atomic weights. So, like for example, this 39.098, that would be the atomic weight of potassium. If we go to our compound, which we have barium sulfate, so SO4, we're going to see 137.33, and then the sulfur would be 32.06, and then we also have some oxygen. Basically, what we do to find the molar mass of our compound is add up all those numbers. So let me see. I have my calculator over here. If you guys could also grab a calculator, that would be great. All right, and we're going to calculate this. So we have our BaSO4 and Ba being right here, 137.33, plus our sulfur, 32.06, plus our oxygen. I'm just gonna call that 16 because by that point, really, it's 16. Most times when you're doing your calculations, you're just gonna call oxygen 16. But we have that, and of course we'll have to, I wrote 3, which is not correct, sorry. Multiply that by 4 because we have BaSO4, we have 4 oxygens there. Calculating the atomic mass of something is literally just this straightforward. As long as you have your periodic table, you just read off those numbers. At one point, if you're very familiar with chemistry, you might start knowing some of these masses, some of these atomic weights by just memory. But at this point, we can calculate it with our periodic table. So does anyone have that number? What our atomic weight is?
Yep.
All right, what do you have?
233.386, but I used 15.999, so
Oh yeah, that's perfectly good. Since I am a bit of a lazy poke and I did not use the 15, I got 39. These numbers pretty much the exact same. But I'll go with, I think you said 386. I'll go with 386. So let's go back to our other thing. And all my work's gone. That's fine. We'll figure it out. So with this one, I'm going to quickly write out our balanced net ionic reaction. Net ionic meaning we're cutting off all the things that aren't really participating in this reaction, like the copper and the nitrate. And now we have our mass, which I think was 233.386. That's
Yep.
And I'm gonna put the units on there, grams per mole. That we'll talk about what moles are in probably like 10 more minutes. But what we have here is we'll then have to divide the total mass by this number. So how would we find the total mass? Now, this is an AP kind of thing where they try to give you a chart, and then you have to interpret the chart. In this case, we'll find our mass by looking at these two numbers right here. Mass of this filter paper, which the student was using, if we remember the scenario, they're using a filter paper. And the mass of the filter paper and dried precipitate, so our actual solid. The precipitate just means solid that we took out of water. And subtracting these, we get the mass of our solid. So can someone do that for me real quick and tell us what number we get?
.372.
0.372. All right, thank you. And that's going to be in grams because that's going to be our mass. We do see grams over here. So once we do this kind of calculation, we can finally get our number of moles. So at the end of this, we have grams over moles. Now, if you have gone to more complex fraction manipulation in math, then you'll know that grams per mole just means that the mole comes up and the grams cancel. So we're ending up with moles as our units. Shoot. Whew. Almost delete everything again. But anyway, let's do that calculation real quick. This one right here, 0.372 divided by 233.386. And what I get is 1.59 times 10 to the negative third. I'm putting this in scientific notation because that's more convenient for this case. I could also write out 0.00159, but I prefer the scientific notation, a little more elegant. Anyway, that's in moles. And from here, we can calculate the molarity. Now, molarity, we haven't really talked about that yet. Does anyone know or have a guess for what molarity might be about?
Yeah, molarity is like the number of moles of solutes divided by the volume of the solution in liters.
Yeah, moles per volume. And That's spot on. So very nice. And I guess an easier way of imagining this basically is concentration. So if you have a lot of moles for a small amount of volume, that's going to be something very concentrated. And if you have very little moles for a large amount of volume, that's going to be very sparsely concentrated. And now I think I've already gone on long enough without explaining moles, so I'm going to quickly explain moles. It's basically just a way of counting. So let's say I have Cu, I have one atom of Cu. Now, that's just one atom, something microscopic. I probably would lose it right away because it's a single atom just floating around. But let's say I have 6.022 times 10 to the 23rd number of atoms of Cu. This amount is what's going to be called 1 mole. You might ask why that number. This number is actually a very special number called Avogadro's number. And Avogadro's number it has some chemically beautiful kind of manipulations to them. But this is how a mole is defined, and this is how chemists have been using it for a very long time. So that's honestly the primary reason why we're still using it today. But that's 1 mole. So when I say I have 1.59 times 10 to the negative third moles, what that really means is I have a lot of atoms. So 1.59 times 10 to the negative third is a small number, but once you multiply it on 6.022 times 10 to the 23rd, I actually have 9.57 times 10 to the 20th number of atoms. Now, you guys could probably already see why we don't count in atoms and we stand count in moles, because counting in atoms means you're going to have large exponents on pretty much everything you do. So that's why we ended up using moles. It's just a lot simpler for our calculations. But this is the number of moles we have. And as Suyang said, he's spot on with his description of molarity. Basically, this number of moles over a certain volume. That volume usually is going to be in liters. So moles per liter is going to be our units for molarity, moles per liters. And we have the moles of our BaSO4. Using this, we'll then be able to find the volume of our CuSO4. Now, this is where that idea I brought up at the beginning, stoichiometry, comes in. So what I'm going to do is, first I'm going to erase this because it's in the way. And then I'm also going to write our complete ionic equation. I think it's called, I think it's just called complete ionic equation, if I'm remembering correctly. It's basically CuSO4 plus BaNO3 2 goes to BaSO4 plus CuNO3 2. If we remember back to our earlier discussion, the 1 plus 1 has to equal 1 later on. The conservation of mass, all of that, that's what this whole problem, this last problem is going to be about. We know we have 1.59 times 10 to the negative third moles just being a counting method of BaSO4. So if that's what we're able to produce, and we know that the reaction goes to completion, mentioned earlier in the problem, then how much CuSO4 must we have had in the beginning? What do you guys think? We know that these are in a 1:1 ratio, right? We can look at the coefficients. Everything's in ones. This is our final amount.
Are you just supposed to look at the chart for this?
Not really. So if we have this amount for this particular compound, and we know that these are in a 1:1 ratio.
Don't they have the same amount?
They would have the same amount, But when we say amount, it gets a little confusing in chemistry because you could say they have the same mass or they have the same number of atoms. Those are completely different things.
Same
So
number of moles.
same number of moles. So yes, they will have the same number of moles. What we have is 1.59 times 10 to the negative third moles of CuSO4. That's what we're going to be left with. They have the same number of atoms because in this reaction, it goes to completion. So that means that they have to be in a 1-to-1 ratio. Now, you might ask, well, we've seen scenarios where it's not the case, where we have, say, 3 atoms of this, 2 atoms of that, and then we produce 2 here. Well, these would not be in a 1-to-1 ratio. Then that requires a bit of more careful observation about the problem. We're actually given the amount of BaNO3 in the beginning of the question. So if we do the calculations here, 0.02 would milliliters, 20 milliliters would be 0.02 liters times 0.2. We get 0.004 or 4 times 10 to the negative 3. So what we're going to see is that in order for this reaction to produce this much product with more of that reactant, the CuSO4 is going to be the limiting factor. It's going to be what limits the amount of product produced. And that's how we're able to know that we're eventually left with CuSO4 of 1.59 times 10 to the negative 3. All right, so a lot of our discussion, I know today is a little bit dry. It's a lot of me talking. And in the future, for next week and going forward, I'm looking to have a lot more participation from you guys. But a lot of our talking and discussion will be also surrounding questions. So any questions so far from you guys? Any confusion about how we know this is 1-to-1?
No.
All right, we're good? Cool. So how we can mathematically represent this 1-to-1 property is by writing it out with a fraction. So let me do that real quick. BaSO4 times 1 mole CuSO4 times 1 mole over 1 mole BaSO4. So if we look at the units, we can see BaSO4 cancels out. We're eventually left with 1.59 times 10 to the negative third moles of CuSO4. So stoichiometry essentially is just that, using these ratio ideas. Now, your equation, of course, is not always going to be a 1-to-1 thing. Like, say I have 2 moles of oxygen over 1 mole of CO2. If we were to take that example from that other combustion reaction, and of course, a lot more goes into it. So that's the basis of stoichiometry, though. So if we know that we're eventually left with 1.59 times 10 to the negative third moles of CuSO4, then we're able to find the molarity, because what we can do is simply look for that volume, which was provided in the chart, and take the moles, divide it by the volume, and find a concentration that way. So I'm just going to take this value, divide it by 50 milliliters, and of course I'm going to convert to liters first, so 0.05 liters. Doing that calculation. And what I'm left with is, does anyone have a value for that calculation? It's okay. 3.18 times 10 to the negative 2 molar. Molar just means moles per liter. That's just a quick way of writing that. Anyway, that would be our final answer for this question. And that's the final result of this question. So yeah, that is an AP chemistry question, 2021. And we just work through it together. So I think that's how I'll mostly be starting out these meetings. I'll put down a question for us to look forward to or observe, read, try our best with, and then talking about our topic for today, and then moving into solving this question. But anyway, anything I missed? Anything that you guys might have questions about for stoichiometry as an idea, or anything we really discussed today?
Can you go over the one-to-one thing again?
One-to-one thing. All right. So let's write out that equation. Oh, shoot. Let's write out that equation. What was it? BaNO3 2 plus CuSO4 goes to BaSO4 plus CuNO3 2. That's what we have. So we have, if we have one of this and one of that, we're going to be ending up with one of that, right? Conservation mass, we're limited by the amount that we put in. The amount we get out is limited by the amount we put in. If we put a 2 over here, we're still going to be limited because BA is not enough, right? BA is still only 1. You can't just create BA out of nowhere just because you have more CuSO4. It doesn't happen that way. So we're still limited. So even when this thing is like 200 or something like that, right? It's still going to be limited. Now I'm going to put moles in front of this because that's the quantity we're working with. Moles just being a large number of atoms. And now we're given that instead of these arbitrary values, we are given that we have 1.59 times 10 to the negative third moles of this quantity. We're also given in the question that we have a certain amount of BaNO3 2. We have 4 times 10 to the negative third moles. The 4 just coming from a calculation over here where we take this molar and multiply it by our volume. In the end, though, we're given that the 4 times 10 to the negative 3 moles is over here, but we end up with less products. So that must mean that this is not the limiting factor. Therefore, we know for sure that it's the CuSO4 that's the limiting factor. So that's going to be the one that is going to be in that 1-to-1 ratio. So it's the same principle as if this were 1 and this were 2, we're ending up with 1 and 1. We know that these will have to correspond because mass is conserved and mass is not randomly destroyed or created. That's where the 1-to-1 thing comes in. And it's not always 1-to-1, of course. So if say like I have, yeah, I'm just gonna go back to that, the combustion reaction real quick, and we'll try something out. Let's say I have 4 of this and 3 of that. How much product would we have? If we can also just draw out the things. 2 of these correspond to 1 of that. 2 of these correspond to 1 of that.
Three.
3 for
Wait,
which one? So
yeah, 3 moles, I guess. CO2.
3. Okay, so 3 CO2.
Yeah.
So what's going on here is that we see that this is a lower number. So then that must mean that's the limiting factor, right? But it's not actually, because we have the 2 over here. We actually need more oxygen. We need twice as much oxygen as methane to be able to have this reaction go forward. So what we're going to see is that this is still the limiting, because having 4 of this means that having 2 of the methane would be enough to react fully, right? Because we'd have 1 of this react with 2 of that, and then 1 of this react with 2 of that. We'd end up with 2 and 4. But what we actually see is that we have 3 here, so that's going to be the excess.
Sorry, I've accidentally mixed up CH4 with CO2.
Yeah, no, don't worry. But that's the idea that we're going with. And it of course gets more complicated as the equations get more complicated. But limiting and which is not limiting, how the products are produced, depending on how it's limiting or not. That's all what we covered today. So that's what's going on here. We have a 1-to-1 ratio between these ones because this one is excess and this one's limited. So that's how we're able to find how much CuSO4 we have. All right. So that's all about stoichiometry. And I did mention that we'd go over a little bit of the bio side of some stuff, going over amino acids, perhaps. That's what I was thinking of. But we're kind of out of time right now. I plan to start with what I was going to end off with today. I'm going to start with that discussion of amino acids because, of course, this is bio-chem, not just chem. Although I will admit I'm more of a chem kind of person, but this is bio-chem, so I will be talking a bit about bio. Anyway, that's today, but actually, I never introduced myself. So my name is Sean Liu. I'm currently a senior in high school, Montgomery High School, and I've done AP Chemistry, AP Biology, but also US National Chemistry Olympiad. I placed in top 50, and in the US Biology Olympiad, placed in top 400. So that's a little bit about me, and chemistry is my thing. So I'm really excited to be talking with you guys about chemistry and also biology, because biology really is just a very vast, kind of fascinating, intricate application of chemistry principles. But anyway, that's our discussion of stoichiometry for today. And if you guys think of any questions, of course, feel free to come to next week's meeting with those, and we'll talk through them and everything. But today, I know it was a little bit slow and a lot of me talking. I really hope to change that going forward. A lot more of you guys being involved, and also the pace moving forward at a more ready rate. But there's always kinks to work out for that first meeting. Anyway, where did I learn chemistry? Well, I did some school learning of chemistry, but a lot of it was also just at home, self-studying. Also studying, I never sent you that form. There was a bit of an intro form that I put together for you guys to consider. So I do want you to fill that out. I'm gonna send it in the chat real quick one more time to you. Just for me to have some information about what place you guys are at with chemistry and things like that. But anyway.
Thank you.
Yeah, for sure. That kind of wraps up our meeting for today. As like I said, any questions, you can also feel free to stay after a little bit if it's a quick question, but also we can continue discussing your questions next week.
Yeah. Sorry.
Yeah. Go ahead.
Just a quick question.
Yeah.
For how do you prepare for the bio and chem Olympiads?
Olympiads. That's a little long. That's a pretty long answer for me to put out there. Well, there's a lot of factors into it. Putting a schedule for yourself, getting the right textbook, find those practice tests online, all of that. Planning ahead. Usually, you do want to plan ahead several months before you start with your preparation. But that is something that if you guys are interested in, I can go into more detail next meeting. After all, this is the Bio-Chem discussion club, discussion emphasis. This is driven by you guys. So what you guys want to talk about and want me to answer, I'll be happy to do so. So if that's what you guys are interested in, I can talk a little bit about that in our next meeting. I'll keep that in mind. All right. But anyway, that basically wraps us up for today. And hopefully I'll see you guys next week, same time. So that's all I'm saying. Anyway,
Thank you.
yeah.
Thank you.
Bye-bye.